It is likely that you have seen a resistor like this in a circuit, or even in a heater. But how does a resistor works internally? First we must clarify the concept of electricity. And for this we are going to use this piece of cable. This cable has electrons, which are subatomic particles of negative charge that can move freely. When a potential difference or voltage is applied between the two ends of the cable, the electrons are forced to move. And it is to this movement that it is known as electric current. However, even though the electrons can move through the wire, not everything is so easy. There is a resistance that opposes the flow of electrons. This is the electrical resistance, and its unit of measurement is the ohm. In fact, since our own body is capable of conducting electricity, we could say that we are a resistor, and even that in these two circuits the resistance is equivalent. But clearly one of the two options is more viable to implement. One of the main differences is that each one has a coefficient of resistance determined by the material of which they are made. In fact, there are multiple classifications depending on this coefficient of resistance. If a material has a low coefficient of resistance, it is said that this is a conductor, such as copper or gold. On the contrary, if its coefficient is higher, it is said to be an insulating material such as glass or plastic. But there are also materials with intermediate values, and these are known as semiconductors, which, in some cases, vary their conductivity depending on other external factors, as we saw in the previous video about diodes. And finally, although they are an extreme case, there are also superconductor materials, which when they are below a certain temperature decrease their coefficient of resistance drastically. We now know roughly how the coefficient of resistance affects the behavior of the material. And if one day we find two cables of exactly the same dimensions but made of different materials, such as, one of copper and one of iron, after having seen a table like this, we could say with complete certainty that the resistance of the iron cable is greater. But, we could not say what is the value of the resistance of any of the two cables, because only that information is not enough to know. Let's focus on the copper cable. The resistance of this cable will be equal to the coefficient of resistance multiplied by the length of the cable and divided by the area of its cross-section. Let's make some analogies to understand more easily how each variable affects. Let's imagine that this cable is a pipe to which we will add two tanks, one filled with particles that represent the electrons, and an empty one, to also represent the potential difference, or voltage that will be applied to the cable. When we close the circuit and let the current pass, we can see how the particles pass without problems towards the other tank. This, because copper has a fairly low resistivity coefficient. Now, if we change the copper for another material like iron, the pipe will have obstacles inside. In this way, when we let the current pass, it will be more difficult, but not impossible to reach the other end. That is to say, it will have a greater resistance. Having an insulating material would be like having the pipe completely covered. The next two variables are easier to understand. If we have a greater distance to travel in the pipeline, it is logical that more time and effort is required to get to the other extreme. That is to say, the longer the cable, the greater the resistance. On the other hand, if we increase the diameter of the pipe, even when the resistivity coefficient continues to affect the entire volume, there are going to be more possible ways for the electrons to pass. In other words, the greater the cross-sectional area of the cable, there is less resistance to the passage of the current. Now let's go back to the real version before my computer melts by doing these simulations. Although this formula is usually used for its simplicity, you should know that the temperature can also affect the value of resistance, since the coefficient of resistivity you find in the tables like this specify the temperature at which that value is correct. Although most metals increase their resistivity coefficient while increasing their temperature, this is not true for all materials. It's important to mention that in reality, almost never will be only one cable between the two poles of a power source, as this could generate a short circuit. That is to say, a sudden increase in the amount of current that passes through the conductor.
This power supply can generate 20 volts 150.
And I say almost, because when you want to generate heat, as for example in a heater, basically that is what is done. This phenomenon by which a conductor emits heat when a current passes through it, is known as the Joule effect. And we can calculate the energy dissipated in the form of heat as the multiplication between the voltage applied to the conductor, the intensity of the electrical current that is passing, and the time during which this occurs. The limitation of doing this is that the material could be melted or oxidize extremely fast, leaving it unusable. That is why for such cases, alloys such as nichrome are usually used, which, in the first place, has a melting point of 1400 degrees Celsius, and also has a high coefficient of resistance. This last characteristic is precisely the reason why only that section is heated and not the cable that we plugged in. Going back to the main topic, now that we know how to get a quantity of ohms to our liking, in theory we could create our own resistance using an extremely thin material with a high coefficient of resistance. But in reality they are not like that. If they were just a wire, it would be extremely difficult to get an accurate resistance in such a small size. There are different ways to create a resistance depending on how many ohms you want to get and how accurate should be its value. The first way is using a nickel wire wound in a ceramic tube, which by the way is an insulator. In this way, you can control the total resistance modifying the length of the cable, but maintaining a compact size. The second option is using a composite material in a defined volume, but that by varying the elements that make it up, you can vary its coefficient of resistance, and therefore the resistance of the resistor. And the third option, is by means of a ceramic cylinder covered by a carbon film, which is cut in a spiral until obtaining the desired resistance. In other words, a carbon wire is gradually created to increase the resistance to the desired value. As generally these resistances are so small, it would be quite difficult to print what their value is. That's why was invented a code of colors, by which we can know its value in ohms, even without numbers. For example, this is a resistor of 200 kΩ. The way to read its value is as follows. The first and second bands correspond to digits from 0 to 9, in this case red is 2, and the black is 0. Then, the third band corresponds to a multiplier to avoid the need to put many black bands when representing large values. In this case, the yellow band means that you have to multiply by 10,000. 0 per 10,000 gives us 200,000 ohms, or 200 kΩ. And the last band that is left, corresponds to the tolerance of this value. As we saw earlier, a lot of precision is required to generate an exact value. In this case, gold means that the tolerance of the value is plus minus 5% of the defined value. May happen that at some point you will find a resistor with more bands, and its reading will vary slightly, but the logic is the same. As you can imagine, it is unlikely that there are resistors of all values, so there are different ways to mix known resistors to get a desired value. The first way is connecting resistors in series, whereby the value of the equivalent resistance is equal to the sum of the connected resistors. This is very easy to remember if we think about the formula that we saw at the beginning. By connecting two equal resistors in series, the only thing we are doing is multiplying the length of the cable by 2, and therefore its value will be double. On the other hand, if we want to reduce the total resistance of a set of resistances, what we can do is connect them in parallel. If we connect two equal resistances in parallel and think again in the formula, we will realize that what we are doing now is simply multiplying the cross-sectional area by 2. That is, we are going to have half the resistance. For more complex systems the way to calculate it is something like this, but the important thing is that you understand why it is like that. At this point I think we are ready to start talking about what a resistor is for. The use of a resistor with a static value in a circuit allows us to regulate the voltage that will be generated in different components. Suppose we have a battery of 12 volts and a LED that works at a maximum of 3 volts. If it exceeds this value, it will burn. In this extremely simple circuit, just by putting a resistor of the right value, we can make exactly 3 volts pass through the LED. In this video I do not want to go into much detail about how to calculate the value of the resistance that we would need. But, if you want to continue on your own, I summarize 3 extremely important laws. The first one is Kirchhoff's voltage law, which tells us that if we add all the voltages following a closed path in a circuit, the value must be 0. Or in other words, the sum of the voltage in each of the components in this trajectory must be equal to the voltage in the power source that is supplying them. The second, is the Kirchhoff's current law, which tells us that in each node, that is to say, where there is more than one possible path for the current that enters must be equal to the one that comes out. And finally the third law is Ohm's law. which tells us that the voltage in a component is equal to the current that passes through it, multiplied by its resistance. Which, by the way, allows us to calculate any of the three variables as long as we have the other two. As I said, a resistance allows us to control the voltage that passes through other components, and there will be times when we want to modify that voltage during the use of the circuit, not only during the design stage. And here is where the potentiometer appears. The way a potentiometer works is using an arc-shaped resistor, which, by adding a point of contact with another terminal right between its ends, act as if it had two resistors in series. In this way, if we measure the resistance between the first terminal and the intermediate one, we will obtain a value. Whereas if we measure the third terminal and the intermediate, we will obtain another value. However, by measuring the resistance between the first terminal and the last, this will always be the same, since they are in series. This feature allows us to generate circuits like this, in which when changing the potentiometer we vary the voltage that passes through the LED. This video had a lot of information, so congratulations if you got here. That's all for now and I'll see you in the next chapter.